Medical technologists often study the distribution of blood types in a population. In order to show the relative proportion of the different blood types, what type of graph are we going to use? Yes, you got it. A circle graph or a pie graph that we usually know. With the use of this graph, medical technologists are able to show the relative proportions of the different blood types.
Welcome to our exploration of the informative world of pie graph. In this discussion, we will unravel both the historical origins and modern-day applications of pie graphs, from their humble beginnings as an early form of data visualization to their pivotal role in today's data-driven world. We will journey through time and purpose to understand why pie graphs remain fundamental tools.
A pie chart is a graphical representation technique that displays data in a cellular shaped graph. It is a composite static chart that is often used to represent sample data with data percentage at a set point in time. Pie graphs serve as a visual depiction of data wherein each segment portrays the relative contribution to the overall total. The entirety of the pie graph invariably sums up to 100%. It takes on the appearance of a round pie that's segmented into portions, where each segment symbolizes a unique category or data elements, the segments being labeled starting with the largest and proceeding to smallest. Since pie charts are typically used to represent data with numerical values, it is important to note that the text you provided doesn't contain specific numerical data. Each segment in the pie charts correspond to one of the key concepts, and the percentages represent the proportional importance of each concept in the overall understanding of pie chart. Pie charts are useful in our daily professional tasks because they provide data in a simple and visually appealing manner, making it as easier to understand proportions and relationships between different aspects. It allows us to streamline complex information in a variety of industry like business, finance, and education. Pie graph improve communication and allow us to respond to data more.
In 1801, a pie graph, also known as a pie chart, was a graphical representation used to display data in a circular format. It was invented by William Playfair, a Scottish engineer and economist. The pie chart divided a circle into sectors, with each sector representing a category or data point. The size of each sector was proportional to the quantity it represented, making it a useful tool for visualizing data and comparing different categories at a glance. Playfair's invention laid the foundation for modern data visualization techniques, and a pie chart continues to be widely used for conveying information in a clear and intuitive way. In 1802 to 1866, the basic concept of the pie chart remained the same: a circular graph divided into sectors, with each sector representing a category or data point. The size of each sector were proportional at the quantity it represented, allowing for easy comparisons. Throughout these years, the pie chart gained recognition as a valuable tool for conveying information, especially in the fields like economics, statistics, and science. While improvements in printing technology and the availability of data played a role in its widespread adoption, the core principles of the pie chart established by William Playfair endured. From 1802 to 1866, the pie graph continued to be a fundamental and effective method for visualizing data, contributing to the development of data visualization techniques that are still relevant today. One notable event in 1858 related to the data visualization was the publication of Florence Nightingale's coxcomb or rose diagram. These innovative charts, which were a variation of the pie chart, were used to illustrate causes of mortality in the Crimean War. Nightingale's work helped to highlight the significance of data visualization in healthcare and statistics. Overall, in 1858, the pie graph had firmly established itself as a valuable tool for representing data in a visually accessible manner, and it continued to be used for various applications, including statistical analysis and scientific communication. Throughout 1820 to 1910 era, advances in printing technology and the increasing availability of data contributed to the widespread use and refinement of pie charts. They were employed in various fields, including economics, statistics, and science, to convey complex information in a clear and accessible manner. One significant development during this time was the recognition of pie chart an effective means of presenting statistical data. Statisticians and scientists began to appreciate the visual impact and ease of interpretation offered by this type of graph. This period also saw the use of color and shading techniques to enhance the visual representation of data in pie charts. During 19th century, as the importance of statistical analysis and data presentation grew, the pie chart gained popularity as a tool for illustrating data in the fields such as economics, demographics, and social sciences. Its simplicity and visual appeal made it a widely used method for conveying information about proportions and percentages. Overall, the development of pie chart in 19th century marked an important milestone in the history of data visualization, providing foundation for the graphical representation of data that continues to be relevant and widely used today. In 20th century, pie charts allowed researchers, businesses, and governments to convey information about various topics such as population demographics, economic distribution, and scientific data. They were used extensively in report, presentations, and publications to help people grasp complex data at a glance. Notable advancement in 20th centuries like the growth of statistical analysis and the computerization of data processing also contributed to the popularity of pie charts. These tools made it easier to collect, analyze, and visualize data, which in turn led to more widespread use of pie graphs to communicate important information effectively. In the late 20th century, pie charts were a common graphical representation used in the field of computer science and data visualization. Pie charts were a widely used tool in the 20th century computer era for visually presenting data. They provided a simple and effective way to convey proportions and percentage, especially when combined with the capabilities of emerging computer software and graphics technologies. Pie graphs are effective tools for presenting complex data in a simple and visually appealing way. In the 21st century, we face numerous challenges such as climate change, global health crisis, and economic inequality. Pie graphs can be used to depict data related to these challenges, making it easier for policymakers, researchers, and public to understand key trends and statistics. Many 21st century challenges require the allocation of limited resources to address them effectively. Pie graphs can illustrate how resources are distributed among various aspects of a problem, helping decision makers make informed choices about where to allocate funds, manpower, or other resources. In summary, pie graphs play a valuable role in addressing 21st century challenges by facilitating data visualization, aiding in resource allocation, raising public awareness, tracking progress, and enhancing policy communication in an era marked by complex global issues.
How to create a pie graph? To create a pie graph, we must follow these steps. Step 1 is data collection. Gather the data you want to represent in a pie graph. This data should be in a format where you know the categories and their corresponding values. Step 2 is to calculate the total. Step 3 is to calculate the percentages. Step 4 is the angle calculation. And step 5 is draw the circle. We start with a blank circle. You can use a protractor or specialized software for precision. Step 5, draw slices. Draw each category slice using the angles calculated in step 4. Start with the first category at the top, 12 o'clock position, and draw the slices in a clockwise direction. Step 6 is label slices. Label each slice with the category name and its percentage or value. Step 7 is color coding. Optionally, use different colors to differentiate the slices and make the graph more visually appealing. Step 8 is title and legend. Add a title to your pie chart, and if needed, include a legend to explain the colors or categories. For the last step, we must review and refine. Double check your chart for accuracy and clarity. Make any necessary adjustments, and then we finalize our pie chart. Once you are satisfied with your pie graph, you can save or share it as needed.
So let's have our sample problem number 1. There has been a survey conducted among 200 of third-year medical technology students at UC Banilod to find out which area of clinical laboratory they would most like to intern in. The pie chart below displays the data gathered. So we have microbiology 16%, phlebotomy 25%, blood banking 22.5%, hematology 20%, and clinical chemistry 16.5%. Now, let's find out the answers to these questions. First, what clinical laboratory area is the most favored among the students? Next is to calculate the number of students in each area of the clinical laboratory. And the last one is that what is the total central angle for hematology and microbiology?
As presented by the chart, we can see and visualize which among the clinical laboratory areas is the most favored. We can derive from the chart that phlebotomy has the highest percentage at 25% among all areas, and therefore it is the most favored clinical laboratory area among the third-year medical technology students. Since we already know which area is the most favored by the students, we are left to wonder exactly how many students would want to intern in the different clinical laboratory areas. To determine this, let's calculate the number of students by multiplying the given number of students with the percentage of a specific laboratory area as shown in the chart and divide it by 100. Let's first start with phlebotomy. Phlebotomy has 25%, so we will multiply 25 with 200 and divide it by 100. We will then get 50. And so, 50 students chose phlebotomy as the clinical laboratory area that they would most like to intern in. We will be repeating these steps for the remaining areas. Blood banking has 22.5%, so we will be multiplying 22.5 with 200 and divide it by 100. We will get 45. So, 45 students chose blood banking. Hematology has 20%, so we will be multiplying 20 with 200 and divide it by 100. We will then get 40. So, 40 students chose hematology. Clinical chemistry has 16.5%, so we will be multiplying 16.5 with 200 and divide it by 100. We will then get 33. So, 33 students chose clinical chemistry. Lastly, microbiology has 16%. We will be multiplying 16 with 200 and divide it by 100. We will then get 32. So, 32 students chose microbiology.
And as we have seen from the results, we can conclude that 50 students chose phlebotomy, 45 students chose blood banking, 40 chose hematology, 33 chose clinical chemistry, and 32 students chose microbiology.
So, in order to find out the answer to the last question, we need to utilize the formula of central angle of data, which is given data over total of data times 360 degrees. So, let's find out the central angle for hematology. That's the first thing to do, to find out the central angle for hematology, because the question is asking for the total of central angle for hematology and microbiology. So again, the formula is given data over the total of data, and our given data is 40, and that is based from our calculations in letter B. So again, our given data is 40, and that is over 200. So our total of data is 200 times 360 degrees, and that is equals to 72 degrees. Next is that to get the central angle for microbiology, our given data is 32, and our total of data is 200. Multiply by 360 degrees, and that is equals to 57.6 degrees. And after getting the central angle for hematology and microbiology, we need to add both of them. So we have 72 degrees from hematology and 57.6 from microbiology, so that is equals to 129.6 degrees.
For letter C, we have there the question, what is the total central angle for hematology and microbiology? To find these answers, we will use the formula central angle of data is equals to the given data divided to the total of data times 360 degrees. And then we will calculate the central angle for hematology and microbiology. So we have the central angle for hematology, which is 40, which is the given data, divided to 200, which is the total of data, times 360 degrees is equals to 72 degrees. And then we have the central angle for microbiology. We have there the given data, 32, divided by the 200 total of data times 360 degrees is equals to 57.6 degrees. Now, to find the total central angle for hematology and microbiology, we will simply just add these two total central angles together. So we have there the 52 degrees plus 57.6 degrees is equals to 129.6 degrees. So the total central angle for hematology and microbiology is indeed 129.6 degrees.
Problem 2 states that a group of third-year medical technology students conducts various types of diagnostic tests in their internship training. There are 60 patients that were collected for each diagnostic test. They want to visualize the distribution of different test categories performed over the course of a month. The data for a specific month is as follows. Blood test, 30%. Microbiology test, 25%. Imaging test, 15%. Genetic test, 10%. The urine test, 10%. And lastly, the other test, 10%. The following problems are A. What type of diagnostic test has the most distribution over a month? B. Calculate the number of patients and the center angles for each test category.
So now we will move on to the solutions of problem number 2. So the first question is,
What type of diagnostic test has the most distribution over a month? So as we can see on the pie graph, we have there blood test 30%, microbiology test 25%, imaging test 15%, genetic 10%, urine test 10%, and other tests which has also 10%.
The answer indicates that blood tests have the highest distribution over the month, accounting for 30% of all the diagnostic tests conducted by the third-year medical technology students during their internship training. This means that a significant portion of their diagnostic procedures involve blood tests, making it the most frequently performed type of test during that period.
In calculating for the number of patients, we have to calculate the total number of patients, which is 60, to the percentage of the specific diagnostic test over 100. For example, for blood test has 30% distribution. So 60 times 30 over 100 is equals to 18. Therefore, there are 18 patients for blood test. So in calculating for the central angle, we have to divide the percentage of the diagnostic test to 100, then multiply it to 360 degrees since we are using pie graph. So for blood test, we have 30 over 100 times 360 degrees, that is equal to 108 degrees. So therefore, the central angle for blood test on the pie graph is 108 degrees. So that same goes with the other diagnostic test that is in the table. For microbiology test, we have the percent of distribution, 25, the number of patients, 15, the central angle is 90 degrees. For imaging test, we have the percent of distribution, 15, the number of patients, 9. The central angle is 54 degrees. For genetic test, we have the percent of distribution of 10. The number of patients is 6. And the central angle is 36. That same goes with the urine test and other tests since the three of them has the same percent of distribution. So the table we provided is a comprehensive overview of the different diagnostic tests conducted on patients, which is highlighting the distribution of percentage, the actual number of patients tested, and the corresponding angles or the central angles representing each test proportion in the database.
Given the table, we can see how the percent of distribution of the different diagnostic tests affect the number of patients and its corresponding central angle in the pie graph. The data offers valuable insights into the significance of various diagnostic procedures, aiding the viewers and readers in understanding the test landscape within this population.
Pie charts have been used since the 19th century to visually illustrate complex information succinctly and understandably. In the clinical setting, health allied workers such as medical technologists use pie charts to visualize and represent data distribution from surveys to diagnostic tests in clinical laboratories. In the given examples, a pie chart is utilized to interpret data without further explanations. Through visual representations such as pie charts, large amounts of information are conveyed most effectively and practically. In a complex sector such as the medical field, using tools that can easily construe data is a life changer due to its efficiency and effectiveness.